One of the applications of the differential equations we've been studying is that they describe the motion of a spring. So we have this spring. This distance is called its natural length. So let's say it's hanging from some ceiling there. And then if we put some kind of mass on the end, it's going to stretch further. And this is assuming that we let it hang, and this is exactly the position that mass hangs in. So it'll hang an extra L naught further than its natural length. This is called the equilibrium position. And let's let y of t be position in meters past equilibrium at time t. So if we pull this object down further and then let it go, it's going to bounce up and down. So y is the distance past equilibrium. So y of t is greater than 0 when the spring is more stretched than equilibrium, and when this bounces up and it's less stretched than equilibrium, we'll say y of t is less than 0. Let's let m be the mass of the object. Let's let k be the spring constant, which tells us how hard it is to stretch the spring. So there's stronger springs and weaker springs. So that's how hard it is to stretch spring. Then other things that are going to be related, that are going to be important in the differential equation, are a constant called c, which is the damping constant. The damping constant depends on the liquid that the spring might be in. It's really measuring friction. So it depends on the liquid or gas surrounding. Or other equipment that might cause friction. And then we have sometimes a forcing function, which is an external force acting on the spring. So the differential equation of the spring motion is y double prime plus c over m y prime plus k over m y equals forcing function f of t. And sometimes we have initial conditions. Usually the experiment we're measuring is we take the string, we stretch it, and then let it go. Maybe stretch it and let it go with a push. So y of 0 is going to be the position of the object, how far we stretched it at time 0. And then y prime of 0 is the velocity with which the object is released at time 0. So initial velocity. Let us say at time 0. Alright, now I don't want to use all of these in the first lesson, but let's look at the spring constant, which depends only on the spring, and do an example with no damping and no forcing function. So the spring constant is defined to be mass times gravity over L naught, which is the distance stretched past equilibrium. So here's the spring without the mass. There it is with the mass. And then L naught is the distance past natural length that this mass stretches the spring. So now this is, I should mention, this is measured in newtons per meter. Or kilograms per second squared. Now we're going to measure the displacement in meters, and the gravitational constant that corresponds to that is 9.8 meters per second squared. So for example, let's say a 250 kilogram mass stretches a spring 0.5 meters past its natural length. So what's the spring constant? So it is 250 kilograms times gravity, so 9.8 meters per second squared, all over 0.5 meters. So dividing by 0.5 is the same as multiplying by 2. So that's 500 times 9.8, which is half of 1,000 times 9.8. Half of 9,800 is 4,900 kilograms per second squared, or if you like, newtons per meter. All right, so let's say we have that spring and we're going to pull it and let it go, and we want an equation for where the object is at time t. So let's assume there's no damping. So with no damping, we're going to get rid of this y prime term. The c is 0. And let's put 4,900 in for k. And then 0.5 in for the mass. So again, dividing by 0.5 is the same as multiplying by 2. So we have y prime, y double prime plus 9,800 y equals, and let the forcing function be 0. But 490 over 25. And I guess we could simplify that further if we divide top and bottom by 5. So that's 98 over 5. Alright, so let's see what this spring does as time progresses. So this is a homogeneous differential equation. The auxiliary equation is r squared plus 98 over 5 equals 0. So r equals plus or minus I square root of 98 over 5. And let omega be the square root of 98 over 5, so I don't have to keep writing it. So the solutions are all, see, so this is really 0 plus or minus that I. So e to the 0x, which we don't need to write because that's 1, times cosine of omega x plus c2 sine of omega x. So it's all possible solutions corresponding to all possible lengths to which we could stretch the spring to begin with, and all possible initial velocities we could get by pushing the object when we let go of it. So which solution corresponds to initial position of 3 meters and initial velocity of minus 1 meters per second squared. So the initial velocity is y prime of 0 equals minus 1. So y of 0 being equal to 3 means that 3 equals c1 cosine of 0 plus c2 sine of 0, which means that 3 equals c1 times 1 plus c2 times 0. So c1 equals 3. All right, now we need to take a derivative before we plug in 0 to the derivative. Y prime of t is, let's see, derivative of cosine is minus sine. So minus omega c1 sine of omega x. Derivative of sine is cosine plus omega c2 cosine omega x. Y prime of 0 equals negative 1. So that would be a push upward because distance 1 is stretching 1 past the equilibrium. Velocity of negative 1 is velocity in the opposite order, opposite direction, which would be up. So y prime of 0 equals 1 means that negative 1 equals, let's see, sine of 0 is 0. Omega c2 cosine of 0 is 1. So that means that c2 equals negative 1 over omega. All right, I'll put the omega back in there. So 1 over omega is 5 over 98, square root of it. So negative square root of 5 over 98. So the solution we want, our general solution is infinitely many curves, which are all going to be trig functions, all going to be, bouncing up and down. So the one we want, which corresponds to initial position of 3, initial velocity of negative 1, is y equals c1 is 3 cosine square root of 98 over 5x. C2 is minus square root of 5 over 98 sine of square root of 98 over 5x. Now whenever the cosine and sine have the same multiple inside next to the x, this is basically your run-of-the-mill up and down sine-like curve like that. So this would just keep bouncing up and down and forever, always bouncing as high as it does low and never shrinking. Of course, that's not possible because there's always some kind of friction going on, whether the spring is in the air or liquid. And that friction, which naturally would make the peaks and the valleys come closer and closer together, comes from the damping constant. So we'll look at that in another video. The end.